Hello and welcome back. In this video we will be discussing divergence and hopefully curl. So first off, what is divergence? Well, the divergence of a system is the total amount of inward or outward flux of a system, of a vector field. So if we were to have a vector field F, which is a function of x and y, the divergence, which can be written like this, is equal to the total change of f in both x and y directions. So you add them together. So how is this defined mathematically? Well, we use the del operator and we say that the divergence of f is equal to del dot f of x and y. So the dot product of the del operator and f of x and y. That would give you df over dx plus df over dy. So that's your divergence. Your divergence is essentially the total rate of change of a system in all directions at a given point. And there was something I forgot to mention. Before we move on, there was something I forgot to mention in the video on the del operator and the video on the Jacobian operator. You can write a little vector down here in subscript to denote the position at which this is evaluated at. So this becomes df of p over dx plus df of p over dy. And likewise, we can say the Jacobian of f evaluated at p follows the same pattern. That's equal to the gradient evaluated at p of f sub 1 all the way down to the gradient evaluated at p of f sub n. So that's just something I forgot to mention. So now that that's out of the way, the divergence is essentially the total rate of change of the function. It doesn't have any direction, it's just the sum. So when the sum of the rate of change is negative, then things are closing in. So right here, the divergence is negative because the vectors are pointing inward and giving us a negative divergence. So it's going inwards towards a point P. However, over here, the divergence is positive because it's going away from a point. So that's how you can visualize it. So yeah, that's divergence. There's another operation we can do with the del operator and a vector function. Let's say we have f, which maps Rm onto Rn, and thus is a vector or a pseudo-vector field. And I want to take the del operator crossed with the f. So in this case, because we go from Rm to R3 because cross products can only be taken with vectors of it can only be taken with a vector with 3 parts. You can't do any more, you can't do any less. It doesn't work then. Because then our concept of orthogonality doesn't make sense anymore when we start throwing in a 3rd or a 4th component. Have 3 components is fine. So essentially, F maps Rm to R3. But of course, M also has to be 3. So F really maps R3 to R3. Alright? So the cross product of F and del is equal to the determinant of x hat, y hat, and z hat, d over dx, d over dy, and d over dz, and f sub 1, f sub 2, and f sub 3. So f sub 1 is the x component of f, x sub 2 is the y component of f, and f sub 3 is the z component of f. So you take this, and this will give you your cross product. Well, not the cross product. This will give you the curl. So you can also write it like this. It's the curl of a vector field, F. But what is the curl? Well, imagine we have a vector field, or a pseudo-vector field. 2 vectors on that field. And we have some more vectors. The curl is essentially a measure of the amount of rotation of a vector field at a given point. So at this point, the curl would be positive. You'd have a positive curl right here, because this would create a counterclockwise rotation if you were to put like a log right there. However, right here you have a curl of 0, and right here you have a curl of 0 because there's no rotational force. It's just in one direction. So now if you were to have vectors like this would be negative, because now it's going in the clockwise direction. So that's what curl is. It's essentially a measure of how much rotation there is in a vector field, how much rotational flux is in the system. So yeah, that's curl and divergence. I hope you liked this video. And until then, I'll see you next time. Goodbye.